Alright, in this video I just want to do a few more examples of integration by substitution. In my introduction to this method of integration, I did a couple straightforward examples, but as you know, not everything in math is straightforward, so we want to see a couple different wrinkles on how we might apply this technique. So again, we said that when I use substitution is when I have a function and its derivative in the same integrand. And we can see we kind of, well, let me just go straight forward with this, and then I'll explain the wrinkle. I'm going to let u equal x squared, and then du will be the derivative of this, which is 2x times dx. Now notice that what I need to replace is I have to replace this right here, right? That's what that product, right? We could rearrange things if we wanted, so it would be sine of x squared times x dx, but that's what I need to replace with du. But I have this 2. So what do I do with the 2? Well, here's the key, is to remember that if I want to take the integral of some constant times a function, that I can bring that constant out front, right? So I've got, it's the same thing as taking the constant out front and then finding the antiderivative of f, all right? So we're going to use that idea here, and because what I want to replace is x dx, let's divide this by 2, and we'll divide this by 2, all right? So when I do that, now I get that 1/2 du equals x dx, and x dx is what I need to replace. And I already said that u is going to be x squared, so what I'm going to end up with then is the integral of sine u times 1/2 du. Now I'm going to take that constant out front, so I'm going to have 1/2 integral sine of u du. Again, straightforward basic antiderivative. It's going to be 1/2, and we know that the derivative of the cosine is negative sine, so this would be negative cosine. The derivative of that would give me sine, and then plus c. So when I do this multiplication, I get negative 1/2 cosine. Let's put our function of x back in. U is x squared, so this is going to be cosine of x squared plus c. Okay, so this is the little wrinkle, is sometimes what you're looking for is not necessarily just the derivative, but some multiple, some constant multiple of the derivative. So in this case, when I take the derivative of x squared, it goes down to x. When I take the derivative of, well, it goes down to 2x, right? But it's just a multiple of x. I can divide that constant out. What I want to make you, what you really need to be aware of is you can't do this with something that's not a constant. For example, if I say 1 over x times x sine of x squared dx, that is not the same. In other words, this 1 over x and the x don't cancel, right? That's not going to be the same as sine squared of x dx, because this x is inside the integral. We're looking for the antiderivative, and this one's not. We can't just cancel them, right? If we could do that, then we could just take everything on the other side of the integral, and integration would be really easy. So that's just, something to be aware of, that what we're looking for is a function and some multiple of its derivative. And in that case, we can divide out that constant and bring it out front. Okay, so that's one example. Now, what we haven't talked about yet is how do I deal with a definite integral using substitution. And there are actually 2 ways. So the first is to notice if I take the derivative of negative 2x, I'm going to get negative 2. But that's just a constant, right? So we can use the same method that we just did before. So if I let u equal negative 2x, then du is negative 2 dx. But of course, we don't have a negative 2 here, we just have a dx. So let's get rid of that negative 2 over here by dividing. Right? So now I end up with negative 1/2 du equals dx. All right? So I'm going to do that substitution. So I'm going to have integral from 0 to 1. I'm going to bring that negative 1/2 out front. This is just going to be e to the u du. Right? And this is about the easiest integral of them all. We know because it's just going to give me 1/2, negative 1/2 e to the, e to the u, too many letters. And actually, I don't want plus c, right? I mean, that would be the antiderivative, but I have a definite integral here. Sorry, so we're going to go from 0 to 1. But I can't plug these in for u because this was in terms of x. So let's substitute back. Go negative 1/2 e to the negative 2x from 0 to 1. And we'll do that substitution. So that's going to be negative 1/2. So I'm going to put in 1. So that's e to the negative 2 minus e to the 0. All right, well, e to the 0 is 1. And if I bring this negative in, it changes the sign of both of these. So that's going to be 1/2. And then that negative times that negative is going to be positive 1. And then minus e to the negative 2. All right. So what do? Well, we did substitution just like we usually did, but before I plug in my limits of integration, I have to put this back in terms of x. An alternative method is to change these limits of integration. All right. We know the relationship between x and u. It's right here. Right. So at this point, instead of sticking with 0 and 1, so just because this is different, I'll put it in a different color. So this is the, I'll say or, and so what we're replacing is instead of having to go back from u back to x, we can change our limits of integration to be in terms of u, and then we can just evaluate. And let's just see that we get the same thing if we do that. So this is negative 1/2, and now if x is 0, so let's take a look at this. If x is 0, then u is 0. So that's going to be my lower bound. And if x is 1, then u is negative 2. Right? And then, so everything's the same. I still have the same substitution. It's just that I'm changing my bounds of integration based on this transformation. All right. Now, the other thing is we know that if we go from something larger to something smaller, we can flip those limits of integration and change the sign. Right? So that will give me a positive 1/2, and I'm going to go from negative 2 to 0, e to the u du. So that's going to give me positive 1/2 e to the u, going from negative 2 to 0. So that's 1/2 e to the 0 minus e to the negative 2, which is 1/2 1 minus e to the negative 2, which agrees with what we got before. So it's up to you which one you would rather do, if you want to go back to x and put in the original limits of integration, or change the limits of integration according to whatever substitution you're making. So you just take those limits, plug them in for x, and see what the limits would be in terms of u. All right, so that's an example of how we would do a definite integral using substitution. Finally, this one's a little bit tricky, and here's why. If we wanted to use substitution, we're looking for something where we have a function and its derivative in the integrand. And notice here, if I were to let u equal x plus 6, then du would be 1 dx, or just dx. So, but I've got this x over here, and what am I supposed to do with that? It doesn't seem like substitution should work in this situation. This doesn't seem like a situation that substitution is made for, in the sense that we don't have a function in this derivative. The issue is, we can't distribute across this radical, right? The square root of x plus 6 is not the same. Square root of x plus 6 is not the same as the square root of x plus the square root of 6. All right, because then I could just distribute this x across both of those and find the integral of each of them. But here's the trick. Although the derivative of x plus 6 is not x, I could solve for x in terms of u here, right? In other words, if u equals x plus 6, then x equals u minus 6, right? And I'll put this in. I'll put in u for x plus 6. So let's just go ahead and come down here and do this. I'm going to put in u for x plus 6. So I'm just going to have the square root of u. And for x, I'm going to have u minus 6. I'm going to substitute that. And then du is the same as dx. Now, this does help us because I can distribute the square root of u across these. So let me clean this up a little bit and show you how. So this is u minus 6. I can rewrite this as just u to the 1/2 du. And now I can distribute across here. So what do I get? U to the 3/2 minus 6u to the 1/2 du. And of course I can do these individually. So the antiderivative of u to the 3/2, I'm going to raise that to 5/2 and divide by 5/2, which is the same thing as multiplying by 2/5. So I get 2/5 u to the 5/2 minus, I'll leave the 6 out front for u to the 1/2. I'm just going to go up to 3/2. Divide by 3/2 is the same thing as multiplying by 2/3. And then I'm going to have my plus c. All right, so let's clean this up a little bit and then substitute back. So I've got 2/5 u to the 5/2 minus 6 times 2/3. That's going to be 4 u to the 3/2. And then let's go ahead and put in u as x plus 6. So this is 2/5 x plus 6 to the 5/2 minus 4 times x plus 6 to the 3/2 plus c. Again, since we know this is supposed to be the antiderivative of what I started with, you could take the derivative and clean it up algebraically and you should get the same thing. So again, this is just kind of a little trick. We're kind of converting this from something where the x plus 6 is on the inside and we can't distribute across, and we're changing it to where, you know, the plus or minus 6 is on the outside, and here I just have a single square root. And then I can do this distribution and just take the antiderivative of each of them individually.